This white needle-like projection, that's the silent of the aphid. Okay? And it's the silent of the aphid that the aphid, you see, the efficiency of any insect as a transmitter comes from how less it damages the plant. Beetles also transmit, but the beetles have got biting and chewing mouthparts. So while they bite and chew, acquiring the virus is not a problem. But when they go on a fresh plant and bite and chew to feed, they actually damage the cell itself where they are inoculating. So not so with aphids. Aphids are these fibers which are very thin, flexible, penetrate from the top and go right through to the core without damaging a cell because they are moving between the cells. They don't move themselves. And the good part here is, if you look at the diagram on the left, the pink part, that's the thing. Aphids have two kinds of saliva. They have one what is called the gelling saliva and one what is called the feeding saliva. And initially, they actually give you the gelling saliva, and as the silent is penetrating, you have the gelling saliva being synthesized, which helps it move in between the cells and does not allow the silent to damage the cell. The silent moves in right across, okay, moves in, and once it reaches the point from where it has to suck the sap, that's the point where the feeding saliva is now injected, and it takes the silent out, leaving the sheath behind. So the sheath behind actually serves to block this small hole. Okay, well, it's sad, but anyway. Now, I'll just take a minute on this diagram that you see on the right, and which is like, so the virus will move up the gut, move through the silent, up into the foregut, and from the foregut and the mid-gut, it crosses into the hemophil, comes back to the salivary gland, moves out into the plant. The reason why I'm emphasizing, and I could have moved to the next slide, but the reason why I want to talk about this is that this is one of the finest examples of co-evolution. The virus protein, surface proteins cannot be recognized by the insect tract. It is the bacteria present endosymbiotically in the aphid which synthesizes the protein called symbionine. And it is the symbionine that has, strangely, it has receptors for both. It has receptors for the virus as well as the gut. And therefore, you have the symbionine picking up the virus on one side and docking it into the gut wall. From there, it exercises, moves the salivary gland, moves back in and then out with the feed. I will not then therefore bother with the details because maybe just 30 seconds on this. I'm not going to details, 30 seconds just to say that this is a variety you will not find anywhere else. Single-stranded RNA, double-stranded RNA. Single-stranded DNA, double-stranded DNA. All the four formats of the nucleic acid are present as zero, independently though, never together, independently, but in case of viruses. And this has great evolutionary significance. Okay. Several proteins, as I said, are encoded by the protein, this thing, so this is what the genome looks like. So we've got like 5 proteins coming out of the DMV genome, and the movement proteins, the one for replication. If you see, when replicase, movement, code protein, none of the proteins here that comes out can help the virus to translate. For translation, it is taking the help of the host completely. And just to give you a replicated cycle of the cells of the DMV, once it enters the cell, the protein shell will be removed, releasing the nucleic acid. It will attach to the ribosomes. So the genome of DMV is directly translatable. This is another very interesting thing. It's analogous to what we call the mRNA. And it's directly translatable. It moves, gives you the replicase. The replicase will give you the negative sense. The negative sense complex will give you the plus sense. And since I didn't go into an explanation of the subgenome of RNA, let's not bother ourselves with that. Just say that the negative sense gives rise to the plus sense RNA, and you will have the proteins synthesized. Once you've got the proteins and the core protein, the full length nucleic acid is there, there is a self-assembly taking place, and the complete body structure is formed. Controlling of the plant viruses, of course, there are some traditional methods that are going on, and which is like if you have a virus, you see, one of the problems, and you see this in the COVID story, you see this everywhere where there are viruses, that you do not have antibiotics working against the virus. The simple reason that the viruses, in principle, are what you call acellular. They do not have a cell. They do not have a metabolism. And so, what do you target? What does the antibiotic do? Because the antibiotics are going to either disrupt the membrane, they are either going to break the nucleic acid synthesis or the protein synthesis or any of the vital functions of the cell. A virus is acellular, so we have a problem. So one of the things, so you alternate host feeds, you breed for resistance, you just burn, incinerate, you burn the infected plants. That's the way, but the more modern approaches are to use resistance genes. You use genes derived from the viruses themselves, so that they qualify under a big group which is known as pathogen-derived resistance. You can use genes for the core protein, for the movement protein, for the replicators themselves. You can use pathogen-associated protein genes or ribosome-activating protein genes to work. Then, of course, the antisense RNA is a vital the opposite polarity of the RNA is present. The moment you have an uncoating of the virus, as we saw in the cycle of the DNV, there is the antisense present that combines, and the moment the RNA goes double-stranded, it can do nothing else. And that's the end of it. Finally, I really got through this. Finally, just to give you an idea of where the viruses come from. We really don't know where viruses come from. There are three hypotheses that are there, as is everywhere. So you have either a progressive or a regressive. Okay, so they either came from more complex things, they simplified, or from more simple things, they became more complex. So one of the things, of course, is that it's progressive, and that is that there were genetic elements, RNA elements, or genetic elements that actually develop the ability to move out of the cells, and then, so that was the first part, and then somehow got associated with proteins to give you a complete virus structure. Okay, so that's one. And the basis for this hypothesis is the similarity of the replication pattern of retroviruses with those of the retrotranscribons. The second, the regressive one, is that the free-living organisms, they've lost the genetic information. So more complex organisms, but they've lost the genetic information, and in doing so, they've lost the ability to translate, and therefore they need an aggregate host. You see, they need a host for their translation processes. So that's, and the evidence for this comes from the giant viruses that, you see, a tuberculosis virus has a total number of 6,300 bases. And look at the giant viruses we are talking about here, 1.2 million bases. So this is really a regression. And lots of functions, therefore, must have been lost in this case, if this was the case. And then finally, of course, the third, that, okay, the viruses came even before the cell was born, right? And this is because the scientific evidence goes on to say that the autonomously replicating RNA was present before. I will again digress for 2 minutes just to make a point here, because this is one of the very interesting cases. This is a thing called a viroid. A viroid is a naked RNA molecule that infects plants, has a size of just about 245 to